of the introduction to CoppeliaSim, and I thought I'll start with simulating a projectile, which we did in the past classes using MATLAB. So the framework is we'll first simulate a projectile with no drag, then I'll show you how to set the initial condition. So the command for that I've written down there. Then we'll graph the projectile. We'll also get the velocity and position during simulation. So why we need that? We want that so that we can do plots and do post-processing. And then we'll eventually put drag and do something similar to what we did in the class. Okay. So before I start, so if you want to download it, it's basically Coppelia. I'm going to send you the link via chat. Okay, please open CoppeliaSim. I send you the link. Once you open CoppeliaSim, this is what you'll see. Okay, so one thing I found about this program is that it's very user-friendly, but there are lots and lots of icons to click, and it can be easily very overwhelming. So instead of trying to explain to you all these things, what they do, I'm just going to use some of them. And I think the way you'll build up sort of expertise is just by playing with the software. So let's start by first creating a ball or a projectile, and then we can launch it. So the way I do this is add primitive shape, and then let's choose a sphere. Okay. So then it asks me for the size. It's essentially the radius of the sphere. Let's keep it as at 0.1. The units by default are meters, so it's 0.1 meters or 100 centimeters. Okay, so that's the sphere. Now, if you want to see what are the properties of the sphere, all you need to do is click on the sphere. So I'm going to click on this icon here. So when I click it, so click the box, and you see that you get scene object properties. Okay. Okay, so of all the properties, let's play with, let's say, the color. You want to change the color of the sphere. So click on adjust color, and that comes off. And there are many things here to change. I'm just going to pick one of them. Let's say the first one, ambient diffuse component, that basically sets up the red, green, blue, that's essentially the color. And so I can move the bar, or I can paste the RGB values. So I mean, you can put any color you want. Just put some bright color so it's visible. Let's say orange. Okay, done. Close this. Close the shape. So that's about colors. You can explore these properties. I'm going to look at the dynamic properties first, okay? Because that's very important. That's what we are doing today, dynamic properties. So here is clicking the dynamic properties shows up this rigid body dynamic properties. So let's click edit material. Okay, so what do we see here is we have bullet properties, OD properties, vortex properties. So what does that really mean? So remember that when we did simulations in MATLAB, we had used Euler's method, we'd used Runge-Kutta ODE4 and ODE4-5. These are different methods of simulating systems. Similarly, in CoppeliaSim, there are different ways in which you can do rigid body dynamic simulations. One of them is bullet. The other one is ODE and vortex. So we'll always be doing simulations using bullet. Okay, it's more accurate than the other two. And so you can basically set friction, restitution, linear damping for bullet, for using the bullet simulator. If you wanted instead use ODE simulator, and you set properties here. So let's not change anything, but I just wanted you to know. Okay, so close this. The mass is 0.5 something. Let's just change it to 1 kilogram. So 1, that'll do it. And then if you want to change things like inertia, uh, then you can put those values here. Okay, I'm not going to change anything. We are not really doing any inertia. We don't really care about inertia in this simulation. So let's close this. Okay, and close this. Okay, so we have a sphere. Let's just change the name to projectile. Okay. So how do you do that? Well, you double click on that, that way it's highlighted, and then you can change the name. Okay, again, so if you are uh, if you want me to pause and show something, just put it in the chat and I can go back. Okay, so you can see here, you can see bullet. So these are the simulators available. They're the same simulators we saw earlier. And then you can choose how you want to do the simulation. There are options like, do you want it to be accurate or you want it to be fast? So this is basically setting up basically the accuracy versus, being real time or not being real time. Then you can set the time step. Okay, so don't change that. We can change that later. But the key thing to do a simulation is to actually click this icon. If you click on that, it should simulate. In fact, once you click that, you see that numbers are changing. Okay, nothing is moving here, and that's because if you place a projectile on the floor at 0, 0, then it will not move because there's no forces acting on it. Right? It's actually turning a little bit, and that's because of the inertia. Okay, I'm going to stop this. So how do you know the X, Y, Z? You can see here on the right side, you have X, Y, Z. So X is represented by red arrow, Y is green, and so on. So RGB, R for X, G for Y, and B blue for Z. If you want to zoom, what you can do is I'm actually scrolling through my mouse to actually zoom this. You can also zoom using these icons here. So this one is for zoom. So once you click this icon here on the left corner, then you can scroll your mouse to go zoom in, zoom out. If you want to rotate, then you click the next one, then you can rotate. And I believe this one is also kind of a zoom. Okay, so that's if you want to go closer and further. Now let's try to make the projectile move in the air. And so one way to do it is to, well, to lift it from the ground. So the way we lift this projectile up from the ground is to click here. Okay, you can see object item shift. So I click on that. Okay, I need to choose what item I'm going to shift, right? Because in a different scenario, there'll be multiple objects. So I'll click on projectile, then I clicked on the shift, object item shift. Now you can see there are multiple ways in which I can do this. I can move it with my mouse. Okay, so mouse translate relative to world frame. The world frame is the thing, the axis stick, which is sticking here. So when I move this, you can see those green lines. That is just showing that I'm moving it along the X and Y axis. So when I move this, on the top right side, you can actually see X and Y change. The Z is not changing. Right? So here, that's because I was changing along X and Y. Okay, if I want to change along Z, okay, I click Z. I indicate that should only move along Z, and then now only moves along Z. So that's one way you can change or you can move the projectile. Okay, there are other ways to do this. So for example, you can go to position and you can set the position. Instead of setting it with the mouse, you can set it by just typing the position. So let's say that I want it to be at X is 0, Y is 0, but the Z should be, let's say 0.5. Okay, so 0.5 meters above the ground. So enter. Okay, so now it's positioned at 0, 0.5. You can see that over here on the right side, 0, 0.5. How to get the menu? Uh, can you elaborate? Do you mean the menu shift? It's over here, object item shift. Does that answer your question? Okay, perfect. Anybody else? So this is important. Please ensure that you get the projectile at 0.5. So again, way to do it, object item shift and go to position and enter 0, 0.5. Okay, so we are all set to get the simulation going. Click on start resume simulation and you can see that the ball dropped. Where is the position reference? The position reference is, well, uh, it's kind of not shown over here, but it's right where my cursor is. Okay, so that's the 0, 0. You can actually show it visually later on. I'll show that to you in some other class, but it's right over here. Okay, so stop this. Okay, if you want to set it up to real time, like how it will be obvious in real time, you can set this. Okay, so you can set real time. So that's how the object will drop, as if it was dropped in real time. Okay, when you don't click the real time, it will just simulate the system and not show it or visualize it real time. Okay, let's stop. Okay, let's zoom out a little bit. Okay, so next thing is, can we impart this projectile initial speed in the X, Y, Z direction like a projectile would? Now, this is something you cannot do with the icons here. You need to write some code. Okay, so I'm going to now show you how to write code. Okay, question. What is the difference between parent and world frame? So when you do multiple rigid bodies, like say 2-link pendulum, then you can specify the coordinates or the position of link 2 with respect to link 1. So in this case, link 1 is the parent frame. So we'll see that later on when we do a double pendulum, you'll have actually a parent frame and a world frame. Okay, so hold on to that till later. We don't need it now. In this case, the parent frame is the same as world frame. Okay, let's write a script. Okay, so how do you get to a script? Well, you can see this icon here. It says scripts. I'm going to click scripts. This shows up. Okay, so I would say insert a new script. So it asks me for script type. So I have these 3 options. Now, I will choose what is known as a non-threaded child script. And it just means that when I do simulations, those simulations have some calculations. What child script non-threaded option does, it basically does all the computations and then passes control to the simulation. That is different from child script threaded, where the simulations and computations are done all at the same time. So sometimes if your computations are not complete, then the simulation will not care about it and just go on. So if you want to do some testing of robots in real time, what will happen, then maybe you want to do a threaded script. But in this case, when we are doing things in simulation, we just want to do it in non-threaded mode. So I'm going to choose non-threaded. Okay, and it says unassociated. So in CoppeliaSim, you can write a script for each and every thing which is on the left side here. You can write a script for camera, projectile, floor, and so on. So in this case, we want to write a script for the projectile because that's the one we want to launch. Okay. Now, unfortunately, this doesn't let me change associated with the projectile, and I think this is a bug. So close this first. And then if you click the script again, okay, then it actually shows up. So then if you go, so you can say that you can associate the script with any of these things. So let's associate that with projectile. Okay, close. So everybody good here? You've got this. So this is going to be important because now we're going to modify the script. If I change the name of the object, then do I need to choose it again? No, you can change it now. So for example, I can change it now right here to whatever I want, projectile one, doesn't matter. So everybody on the same page, you have the script here. Yeah, so the question is, if you change the name of this from projectile to something else, will you have to change that in the script? I have not really tried to do that, like write code in the script and then change projectile if it automatically changes, but we can check that later on quickly, okay? Okay, so let's click on the script, and what you see is 4 functions, right? Sys init, syscall init, syscall actuation, syscall sensing, and syscall cleanup. So instead of flooding you with information about all of them, it's basically these scripts, these functions are called during different parts of the simulation. The init was called initially, and then once it's called, then the actuation basically is where you would write code to add forces, torques. The sensing is where you would put sensors like vision and so on. And then cleanup is before you end the code, you want to clean up any part of the code, and then you basically write code here. So in this case, we are trying to impart an initial speed to the projectile, and so we'll only need to use syscall init. Okay, so how do you kind of write these functions? What you want to do here is, and you want to just bookmark this in your favorite browser, type CoppeliaSim API, okay? And hopefully it will put up this regular API. So click on Coppelia API framework. Hold on. I want to get I want the function list, not the framework. Okay. So I'm going to send this link to you. You can click on that. Okay, so I recommend that you just bookmark this tab. Okay, so that way it's always with you and you can quickly get to that. So this basically is the functions which you can use to write in CoppeliaSim. On the left side are functions in Lua. What programming we are doing, the one which I showed you is actually Lua. And then there is C++. Okay, now you're not expected to be an expert in Lua, because myself, for example, I did not know Lua till I started using this. So Lua is extensively documented, and every time you have a question, it's just a matter of typing down what you want in the browser, and it will show up what to do. So that's what we'll be doing throughout. Okay, so don't worry, don't be afraid that this is a new programming language. It's not that hard. If you know any programming language, for example MATLAB, you should be fine with Lua. Okay, so in this case, there is an option called okay, so how did I figure this out? Well, I actually velocity in CoppeliaSim. So if you have a question about something, just type it. First thing when I was trying to do this, I just searched for a function, init velocity, and then nothing really showed up on this page. So I thought, well, there's nothing here, so maybe I should type it here. So that's what I did. I typed it, and then there's a link. It shows in purple because I already clicked it. If you click it, it actually tells you what you need to do. You actually end up in the forum for Coppelia, and that's pretty much where this and the API is good enough for you to figure out what commands you need. Okay, which program do you recommend to use with API, MATLAB? I actually suggest we're going to do everything in Lua. I'm not going to make you do MATLAB, though you can use, you can actually write functions in MATLAB to do stuff through the simulator, so you'd interface, but I think that's going to be way too complicated, so we just stick to Lua. Okay, so you can see that somebody had asked a question about initial angular velocities. So it looks like this person is using this. So you can try to read this, but it looks like what I need is this particular function. So I'm going to copy that, go to my API function, and try to find it. Okay, so when I find it, it shows up. So this is the C one. I want the Lua one, so I'm going to click on that. So when I click on object float properties, let me send this through. So you can see that there's a description, there's a C description, and there's a Lua description. Okay, I'm just interested in the Lua one. So sim set object properties. I'm just going to take this, copy that, since I'll be using it. So copy, and then paste it in my code. So I need to paste it here. Okay, I've still not written down things, but let's see how to write this. So for that, we need to again look at what exactly is going on here. There are three inputs: object handle, parameter ID, parameter number. Now, object handle is something which you will be dealing with this simulator again and again. It's basically, this corresponds to the projectile object we created here. So the way to define an object handle is, and this is something which, as I said, you will do again and again. So let's define a projectile handle, and that's going to be sim.get object handle. And here the name would be the name of, its projectile. So if that was called sphere, then I would put sphere here. So this is the handle, and this handle is my first argument. So I'm going to paste it here. Okay. The next thing here is parameter ID. Okay. So what is the parameter ID? So it says here, parameter identifies identifier the parameter to retrieve. See the list of all object parameter identifiers. So let's click on that. Okay, and then this basically throws up all the parameters, and that's really too much. So I'm just going to search for initial. Okay, so when I do this, it looks like I can set the initial velocity by setting up 3000. So that's how you identify this. You could either give this name, or you could put 3000. Let me just go with 3000. So 3000 is for velocity next, 3001 is velocity y, 3002 is velocity z. So what I need to do is here put $3,000. Okay, and then I need to set up initial velocity. So let's just set it to this is x. Let's set it to 0. Okay, so copy this. I'm going to send it to you through chat in a bit, so you don't have to worry if you've not got this, you've not typed this. And this is the z, so let's give it 10. Okay, so here is the code which you want to copy in the syscall-init. Okay, so I'm hoping you've already copied that in syscall. Close that, and now let's click on play. Okay, start resume simulation. So you see it just disappeared from the screen and fell down. You couldn't quite see the whole path, so I'm going to zoom out. Okay, and well, of course, stop this, zoom out, and then play this. Okay, so that actually imparted a z speed. As you saw, it sprung in there and fell down. Okay, did at least few of you tell me if you were able to get that going the way I've shown it. Okay, one person got it. Okay, some. Okay, looks like many people are getting it. Okay, great. So let me just show you how to put comments. If you want to put a comment in Lua, then this is what you do. You put double hyphen, and that's a comment. So this is a comment. Now, sometimes you might want to, put a comment which is, so let's say I wrote, this is a long comment, right? So this is like 4 lines long, and you just don't want to put hyphens all the time. So what you can do is, there's a way in which you can put a comment to 4 lines by using this particular command, hyphen, two square brackets which are open, and then 2 square brackets which are closed towards the end, and then hyphen again. Okay, so this is how you put a comment for a chunk of code. Okay, so again, it's like this different way of doing things. You just have to get used to it. Let's stop, get back to CoppeliaSim. So far we've shown that we can get the projectile to launch. Let's impart some velocity in the, so if you see here, that's Z, and if you do Y, then it's going to go away from the screen. So let's just put some velocity in the X direction, okay? So let's open the simulator, and then let's say put 1, because if you do too much, then it will go away from the floor. So that's 1 meters per second in the X direction. Close that. And now you should see that it actually goes, and it fell down, right? Because the floor ends over there. If you want to actually change the floor size, you can actually click on this icon here. So you can see, you can widen it. It's right now 5 meters, but you can make it, it's here extended in the X direction, and here it's extended in the Y direction. Okay, maybe that's too much. Let's just increase it by 10. Okay. So run this, and then it keeps going, obviously, because you imparted an X speed, and that X speed will take it to the end of the floor. Stop this. Okay, so now I'm going to show you how to essentially make graphs, okay? And that's kind of useful to visualize this. So we need to find the graph icon. So it is here in add graph. So let's click on graph. Okay, and so this thing opens up. So there's a preferred position, and I think I want to put the preferred position to be bottom left. So right now it's bottom right. So when I put it there, then it interferes with my simulation. So I'm going to put bottom left. So it moved to the bottom left. And I think that's about it. Don't need to change anything else. Okay. So we said that. Now we need to basically tell it that this graph corresponds to the motion of the projectile. So that's another step. Let's try to set that up. Okay. So I just clicked on graph. So when you click on graph, the icon, you will see something like this. Okay, so what I need to do is add a new data stream. So I click on that. And now it gives me a list of things I can do. I can take the position, vision, so on. I just want to plot the X and Z position, right? Because it's moving in the XZ plane. So let's choose X. And it's asking me for which object. So in this case, the object is projectile. So select those two. And then say, okay. Okay, so how did I get here? I clicked on that graph icon to get here. Next, I want to add a data stream corresponding to the Z position. So again, add new data stream. I'll click on Z position, and then I'll link it to projectile and say OK. So I have the X position and Y. Let me just call this X and this one as Z. So that'll make it easy to identify them. Okay. What I'll do is, so this by default will plot the X versus time and Y, Z versus time. So let's just first play this. So when you play this, on the left side, you see you have time and then you have X and Z, but we can't distinguish X and Z because they are both red. So let's change the color. So stop, again, click graph. Okay. Click on one of them, let's say X, and you can see adjust curve color. Just click on that and change that to say blue. Okay, close this and then run the simulation. So you can see one of them now is blue, clearly the X one, and the other one is red. So sometimes you want to not show graphs versus time, but you want to show one variable versus the other. So for example, the Y versus, the Z versus X, right? So that's basically the path followed by the projectile. So you can actually do that using the XY graph. Right now, the XY graph is showing nothing. That's because I've not told Coppelia what I need in the XY graph. So let's set up the XY graph. So close this, stop the simulation, go to graph. Here you can see that there is an edit XY graph. So let me click on that. This shows up. So we need to add a new curve, and that curve is going to be something for the X. So let's say that the X value is actually X and the Y value is Z. So select that. And if you want, you can adjust the color, but let's just keep it to the default because there's only one. So close all of that and then run this. And now if you click XY graph, you see that that's the graph of Z position versus X. Okay. I'm going to stop this. Here, if you want to export data to a file so that you can then read it through Excel or MATLAB, then you can actually export the data by clicking export, selected graph as CSV, and then you can, let me just choose an icon that, so I want it in MATLAB, so I'm going to choose my MATLAB folder. Okay, let's call it something projectile, then save. So if I now open my folder and look through what I'd saved, if I click on that, what I get is this. So it basically gave me the time, the X position, and the Z position. So once I have this, there are ways in which MATLAB can read a CSV file. So I can make this in MATLAB and then do whatever plots I want to do. Okay. So this is one of the easy ways of taking data from Coppelia and plotting it in MATLAB. Okay, so we did graphs. Let's now get to setting up the drag force. Okay, so before that, well, in order to set the drag force, we need to find the velocity because the drag force depends on velocity. So by default, what is set in the simulation is just gravity. You can only set, the gravity is set to be in the Z direction, and drag forces need to come through the code. So what we need to do is basically set actuation, code in the actuation which will add the drag force. So before we set the drag force, we want to find the velocity. And again, if you want to find the velocity, your best resource is to go to the API frameworks. Go here, API framework, which is right there, and then search for velocity. Okay, so this is set target charge. get joint targets. There's no joint here, so we'll skip that. Go to the next one. Get object velocity. That seems like the right thing I want. So click on that. So we have get object velocity. So this command looks like this. Okay. So it provides me, if I give the shape handle, so in this case, the projectile handle, then it will give me the linear speed and the angular speed. So I'm going to copy this, go to actuation, paste it. And here, the first argument is going to be project handle. So I'm just going to copy that here. So it's telling me I want the velocity for projectile. And then there'll be two outputs. So one of them is V and the other is W, or let's call it omega. Okay. So now if I want to print or see what it is, I just do print V. Okay. So this is how you call display or show things in Lua. You just say print and the variable name. Okay. So let me send this to you via chat and you can paste it. Somebody asked for the link. The link for this is right here. Okay, so now I'm going to run this. And if you've not seen this, here is where you will see the output. This is just like the command window. So run this. Move it up. And you can see it's actually printing the velocity. So let's stop this. And now you can go back in time and see what exactly did it do. So it started with 0, 0, 0. That's the velocity initialized to 0, 0, 0. Then the velocity kept increasing in the z. So the z velocity was set to 10. So you can see that it's actually decreasing because it's going up against gravity. And the x speed is, well, it should be 1. If there is no forces, it remains close to 1. Okay. Okay, so that's getting the velocity. Now, if you want to add a force, okay, looks like I'm running out of, give me 2 minutes and I should be done with this part. So the way you find a force is so I'm going to go maybe 2 minutes over time. Okay, so bear with me. So we can complete this and I can post this. So we'll get the magnitude squared. So that is basically velocity 1 square, velocity 2 square plus velocity 3. And the reason I'm getting the velocity square is because my drag force depends on the velocity squared. Okay, so my drag force is dependent on a constant, and we call it 0.1. The force in the x direction is minus c, the drag force, times velocity in the x direction, times v mag square. How did I get it? Well, if you look at my notes, you saw that the velocity, the drag force is c times the x dot times square root of x, times x square plus y square. And that's pretty much what I wrote there. So fx, fy, fz, and this will be 2 and 3. Okay, good catch. Okay, and then the command which is used to get add the force is called, and the way I got it is actually got it from the same API framework, is called sim add force. You need to give the project handle, the force, and the torque. So in this case, force is equal to, so if you want to have an array in Lua, then you need to put the curly brackets, so fx, fy, fz, and then torque is going to be 0, 0, 0. I'm not adding any torque. Okay, I'm going to send this to you chat so you can copy it. And let's see, let's run this. So you can see it actually slowed down quite a bit. In fact, if we stop this and we look at the speed here, so it started with 1 and 9.73. but then the speed quickly decreased in the x direction. It also decreased quickly in the z direction, obviously because of gravity, but also because of the drag force.